In this video, we're going to go over some of the most common types of questions and some of the skills associated with the topic of ionic compounds. So as we've already talked about ionic compounds, we usually consider them as being compounds formed between metals and nonmetals. Although if we bring in polyatomic ions, then we can also have compounds that are really made of only nonmetals in specific situations. But mostly we think of them as metals and nonmetals, and they form when there's a big enough difference in electronegativity, a difference that we generally take to be about 1.8 or greater. If the difference is so large when these two elements come together, then when they react, the nonmetal that has a very high electronegativity, high Z effective, will tend to steal electrons away from the metals, and that will form positive ions for the metals after they've lost electrons, and negative ions or anions for the nonmetals. And once we have the positive cations and the negative anions, then those two things will have an electrostatic attraction between them, and that will become the ionic compound. So as a review, the ionic bond is the electrostatic attraction between the positive and the negative ions. And then the structure of the ionic compound is a crystal lattice where the positive ions are surrounded by many negative ions and the negative ions are surrounded by many positive ions. Now, overall, ionic compounds balance out the charges and have no overall charge because of the ratio of the ions. So we'll see that as we do our chemical formulas. One of the most basic skills that you need to be able to describe, it's very simple, and it's based on you knowing the charges of the ions. You need to be able to describe the electron transfer that takes place when ionic compounds form. So if I skip ahead to the next slide, just to review, we reviewed these ion trends when we did the periodic trend topic. So we know that group 1, all of these elements have one valence electron. That means that when they form ions, they always form 1 plus ions because they tend to lose that one outer valence electron, which will give them the stable noble gas configuration from their inner shells. In group 2, they form +2 ions. In the middle, in the D block, they can form variable charges or have variable oxidation states, we sometimes say. So for now, we're going to skip past those. And then in group 13, we have our +3 charges. So these elements tend to form +3 ions. We don't really need to know much about group 14 in terms of their ions. While it is possible to have ions with carbon and silicon, we usually don't see them. We usually see these elements in covalent compounds. The metals down at the bottom, tin and lead, Sn is tin and Pb is lead. They are metals and they will form positive ions. And as you might predict, they can form a +4 ion. They also can form +2 ions. But as a general group trend, group 14 is sort of one you don't need to worry too much about. We know that the noble gases don't form ions, so you can consider this sort of the zero charge column. And as we go left, the halogens, group 17, have 7 valence electrons. So when they form ions, they will gain 1 electron to fill out their outer shell, which will give them a -1 charge. In group 16, they will gain 2 to form -2 ions, and in group 15, they will gain 3 to generally form -3 ions. So that's a review of the ion trends from the periodic table. And if you know that, then it should be really easy to describe what's happening when ionic compounds form. So when sodium and chlorine react to form sodium chloride, if I need to go look at the table and I find sodium. Sodium is in group 1, which means it's going to form a +1 ion, and chlorine is in group 17, which means it's going to form a -1 ion. So in terms of describing the electron transfer, I first think about what change has happened. Sodium went from being neutral to being Na+. So that's a change of 1. And if something becomes positive, that means it's lost an electron. So each sodium atom loses 1 electron. That's all you have to say. And for chlorine, chlorine starts neutral and becomes Cl-. So that's a change of 1. And because it's becoming negative, it must be gaining negative electrons. So each chlorine atom gains 1 electron. And if you can come up with these two phrases, then you've actually earned an IB mark. It's a very easy type of question. If all you really have to do is keep the number of electrons straight, so the fact that it's a 1 plus charge means it's a 1 electron change, and then that the one idea that that does confuse people is that because it's a positive ion, it has lost an electron. So although that's a bit backwards, we remember that electrons are negatively charged, and so they sort of work like negative numbers in that by subtracting them, your charge actually becomes more positive, and by adding them, gaining them, your charge becomes more negative. We could do the same thing for calcium and chlorine. If you look at the periodic table, calcium is right here in group 2, so calcium is going to form a +2 ion, and we already did chlorine, it's going to form a -1 ion. So if you look back, that means that calcium should, when it reacts with chlorine to form calcium chloride, that each calcium atom, which has no charge, is going to turn into calcium 2+. So that means that each calcium atom loses 2 electrons. Chlorine, as we did before, gains 1 electron. Now, you could probably see that that's not exactly balanced, and as we'll see in the next topic, when we're figuring out the formulas of these ionic compounds, we're going to have to balance the number of each ion so that the electrons are balanced and that the overall charges are balanced. But in terms of describing electrons, electron transfer, you always describe it in terms of what's happening for one atom of the metal and one atom of the nonmetal, and the metal is the one always losing the electrons, the nonmetal always gains, and then the charge tells you how many electrons are being lost or gained. The next topic is figuring out the formulas of ionic compounds. This is also, it's related to what we just did. It's really very simple. Really, it all comes down to knowing these charges, these trends for the groups, and then being able to balance the charges. So if you had to figure out the formula of the compound made from potassium and oxygen, you go find the symbol for potassium, which is K. So K is going to form a +1 ion. And then you find the oxygen in the table. Oxygen is -2, and therefore we add 2- as its superscript. So when we write ion charges, we always do the number first, followed by the sign, so 2-. When something has a 1+ charge or a 1- charge, we usually just write a plus or a minus symbol as a superscript. It's not wrong to write a 1+, but it's easiest just to write a plus. So if you can see, right now I've got 1 positive charge and I've got 2 negative charges, and clearly overall that's not balanced. So if I'm going to balance this thing, I can't change those ion charges, but I can change how many of each ion I have. So really I'm going to need 2 K pluses to add up to 2+ charges total, and then I'm going to have 1 O2-, which will give me 2 minuses total, and those will cancel. So as a formula, that's going to work out to K2O. So I have 2 Ks and I have 1 O. Again, in an ionic compound, this is not actually a molecular formula. There are no little K2O molecules bouncing around. Ks and Os exist in a large crystal lattice with millions and millions of ions surrounding one another. All this gives us is the ratio. So this is really an empirical formula. There are 2 Ks for every 1 O. Another simplified way to do this is if you line up the 2 ions, and I call this the crisscross applesauce method. All you have to do is take your little marker here, and the charge on K is 1. I'm going to bring that down, and that's going to be the subscript on O. And then I take the 2- of oxygen and I bring that down, and that's going to become the little subscript on K. And so if I cross their charges, I end up getting the correct subscripts. So the 2 of the oxygen becomes the subscript on the potassium. The 1 of the potassium charge becomes the subscript on the oxygen, and I get the same formula that I got the other way, thinking through how the charges would be balanced out. So again, I'll do it one more time. Let's do number 3. If I get calcium, calcium is in group 2 and therefore it forms a 2+ charge. Nitrogen is in group 15 and therefore forms a 3- charge. So if I can try to figure out, okay, when are 2 and 3 going to be balanced? I can think about the common denominator would be 6, and so I've got to get them both to 6+ and 6-. I can do it that way, but if we just do the crisscross method, which I think really is usually simpler, Then I bring down the 3 from the nitrogen. I bring that down as the subscript of calcium, and that becomes a little 3. I bring the 2 from the calcium's charge down to the subscript of nitrogen, and that becomes 2. And then I get a balanced ionic chemical formula. By having 3 of the 2 pluses, I do get 6 positive charges. And over here for 2 nitrogens, 2 times 3 minus, I get my 6 minus charges. And so overall, this is a balanced ratio. The only time where the crisscrossing sort of doesn't work, it's just something to be aware of, is when the charges are equal. When the charges are equal, then the formula is actually already balanced, and therefore you don't need to crisscross. So in this example, the formula of when magnesium and sulfur come together is just MgS. Because Mg was 2 plus, S was 2 minus, these two ions are already balanced when they're in a 1-to-1 ratio. I don't need to write Mg2, S2, because that would not be an empirical formula. And ionic compounds, their chemical formulas are always empirical formulas. They're always the simplest ratio possible. So then if we combine the different things that we just talked about with the formulas and with what we know about diatomic elements from a previous class, we can write the actual correct chemical equations for forming ionic compounds from their elements. Okay, how does that go? Well, if I'm going to take potassium and oxygen and react them together to form potassium oxide, the compound that forms between them, well, potassium is K, and oxygen is O2. So the first tricky part of writing a chemical equation here for the formation of an ionic compound is remembering that the nonmetal, in most cases, is going to be a diatomic element. So don't forget the little 2. That's one easy place to miss the mark. Then in the formula, I've got to do what we just did on the previous page, which is crisscross or somehow balance the charges to figure out the formula of the ionic compound that forms between these things. So again, we already did this example. Potassium and oxygen, I look at the groups where they are, I figure out their charges, and I can do either method to get the balanced ionic formula, which is K2O. So that's the chemical formula of the ionic compound. Now at this point, I cannot change any of the subscripts. So this has to be a little 2 next to K, and this has to be a little 1 next to O. That's the empirical formula, the balanced chemical formula for the ionic compound. So now my job is to balance the overall chemical equation. I can already see that I've got 2 O's here and only 1 over here. I've got 1 K here and 2 over here. So I'm going to start by putting a 2 there. 2 oxygens, so I need 2 oxygens on the right-hand side. So I am allowed to add coefficients. Now I have 2 oxygens on both sides of the chemical equation, but now I have 4 potassiums here, so I'm going to add a 4 there. So the way I'm allowed to balance the chemical equation is by adding the large coefficients, not changing the subscripts. So now I've balanced the overall chemical equation. If I had written in any little plus charges as I was going along to try to figure out how these things balance, like crisscrossed, at this point, I'd want to make sure to erase or scribble those out because the final chemical equation should not show any charges because this is an overall neutral compound and these are neutral elements. So erase or scribble out any charges that you wrote in or rewrite the equation so that it doesn't show any of those charges. The last step would be always try to add in state symbols, whether it's solid, liquid, gas, or aqueous. So metals usually are solid. That's a pretty good guess if you're not sure. Nonmetals are often gases, or at least things like oxygen and nitrogen, you probably are aware of, are gases. And ionic compounds at room temperature will always be solids. It's usually not a mark, but it never hurts to try to write in state symbols if you can. So that's writing chemical equations for the formation of ionic compounds. And the last little bit is naming ionic compounds. Naming ionic compounds, you've already heard me do it in this video. It's really very simple. The names of the metal cations are named just like the element. So calcium, when it's an atom, is called calcium, and calcium, when it's a 2+ ion, is still just called calcium. Nonmetals, usually end in "ene", like chlorine or fluorine, but they also have other endings like oxygen, hydrogen, nitrogen. But when they get put into compounds, they always end in "ide". So when calcium and chlorine react together, they form something called calcium chloride. When calcium and oxygen react together, it forms calcium oxide. So simply to name an ionic compound, you just have to remember about that "ide" ending. That tells you that they are together as a compound. Now, there are going to be some other endings to worry about when we start to deal with something called polyatomic ions. There are some ions that are formed with multiple atoms being put together, having overall charges. I've listed them in red in the table below, and they have names and formulas and charges which you will be responsible for memorizing. So not all ionic compounds will end with an "ide". Some of them will end with "ate", and so 8 is often a trigger to let you know there's actually a polyatomic ion in the compound. But we'll look at examples with these polyatomic ions in class for the actual naming. So those are most of the skills that you'll have to do with ionic compounds: describing electron transfer for each atom, figuring out the balanced chemical formulas between two elements when they form an ionic compound, and writing balanced chemical equations for when the elements react to form the ionic compound. And then finally, there's naming and getting formulas from names, which is a foundational skill for the topic of ionic compounds, and we'll do some more practice in class.